Very often, so-called symmetric solutions can be observed when formulating a model. Looking at a small example will make clear what that means. Consider what is known as the bin packing problem. On the one hand, we have a set of n identical bins which have a capacity of B. And on the other hand, we have a set of k items and item I has an item-specific weight Wi. We want to put all items into the bins such that the number of bins in use is as small as possible, taking into account that the total weight of the items in a bin does not exceed the bin's capacity. In the example shown here, we have 4 bins, each of which has a capacity of 6. Furthermore, we have 5 items and their weight is given by the numbers shown. A feasible solution would be to put the items into the bins like this. A better solution would be this. It's easy to see that the second solution is optimal. You can't do better than using 3 bins. Before we proceed with our example, we can try to formulate a model for the bin packing problem. As an exercise, you may want to try this by yourself. In that case, you should pause the video now. To model the bin packing problem, you could use 2 kinds of decision variables. You could use a binary decision variable yj to indicate if bin j is used or not, and you could use another binary decision variable xij to indicate if item I is put into bin j or not. In the objective, we can then count the number of bins in use. This counter should be as small as possible, of course. As a constraint, we need to state that each item must be put into 1 bin. Also, we must make sure that the capacity of the bins is not exceeded. The domains of the decision variables have been mentioned already. Now check by yourself if this model correctly describes the situation. Take your time and pause the video now. The model is not correct yet because there is no link between the x and the y variables. According to this model, we could put items into a bin and at the same time we could assign the value 0 to the bin's y variable, which doesn't make much sense. One easy way to fix this is to add y to the capacity constraint. Now, if yj equals 0, no item can be put into bin j. Or the other way around, if we want to put something into a bin, the value of the corresponding y variable must be equal to 1. Recall that we have seen this modeling technique in previous videos already, for instance in the video on Big M formulations. Coming back to possible solutions, look at solution number 3 now. It should be clear that the third solution is pretty much identical to the second, since all bins are identical. The only difference is that in the second solution, the bins 1, 2 and 3 are used, while in the third solution, the bins 1, 3 and 4 are filled with items. The items that share a common bin are the same in both cases. This phenomenon is called symmetric solutions. Applications where you have to deal with identical objects that are randomly numbered, bins in our case, are good candidates for showing symmetric solutions because you can arbitrarily renumber the identical objects to reach a solution that is technically different, but it's identical from the application's perspective. Our example has 24 optimum solutions that are symmetric. The question now is if symmetric solutions are problematic. And the answer is, it depends. It depends on how a model is solved. Sometimes a situation with symmetric solutions will cause the solver to do a search in a wide solution space, checking basically the same solutions over and over again. This would be a waste of runtime, and you could try to modify the model a bit to eliminate symmetric solutions at least to a certain degree. We will come to that in just a moment. On the other hand, modifying the model often destroys the structure of the problem, and the solver's performance declines facing a not so nicely structured model. Especially when you use a commercial software package, you often do not know in detail what the solver does. Finding out if symmetric solutions are problematic is then a matter of experimenting with different model formulations. To give you a hint what some authors do if the application is prone to symmetry, here are some ideas for the bin packing problem. Perturbing the data in the objective function is one way to eliminate symmetric solutions at least a bit. In our application, for instance, we could give each bin a different positive price so that using a bin with lower price is preferred over using bins with higher prices. A simple example would be the following objective. In this case, the price of each bin is the bin's number. In an optimum solution, we wouldn't see any gaps like in solution 3. Modifying the objective, however, must be done with care. An optimum solution for the modified model should also be an optimum solution for the original model. Make sure to understand that the suggested modification still minimizes the number of bins used. A second idea to eliminate symmetric solutions, to a certain degree at least, is to add additional constraints to the model so that some solutions are not allowed anymore. In our example, for instance, we could add a constraint that makes sure that the total weight of the bins decreases with the bin's number. Formally, this can be couched as follows. Note that only 2 out of the 24 optimum solutions remain after adding these constraints.